there's our reaction. Weak base, I have a reaction. Weak base has to have a Kb, has to have a numerical value. So next thing we do, look up the Kb. We have a table for Kbs. The value for this one, 4.4, 10 to the minus fourth. So we'll look that up. Next thing we can do is we have a reaction and a Kb. We should write what Kb stands for. It stands for products over reactants. So our 4.4 10 to the minus 4 equals, on the product side, we have CH3, NH3 plus, OH minus, CH3, NH2. We disregard the water. Just like the weak acid problem, we have to put in values. We need an ice table. We need to know what goes into that. Let's do the ice table. Initial change equilibrium, CH3, NH2 plus water. You know, again, I'm not going to worry about it. Goes to CH3, NH3 plus. Is we're starting with a 0.33 molar solution of the methylamine. That means this guy was 0.33. We assume none of the original products were present. Zero these out. Everything else is X. We have the ice table equilibrium results. We marry those back to the 4.4. 4.4 times 10 to the minus fourth. X, 0.33 minus X. We're back to the same point. Quadratic, yes or no? Take a shot, do yourself a favor, go for the assumption. Try it, it's always worth a try. We're gonna try the assumption, which would tell me 4 to the minus fourth equals X squared over 0.33. We'll disregard that minus X, we're saying that's negligible. We do the assumption, we're saying this guy doesn't count. Not enough of that breaks down to change that number appreciably. That's the case. Got that. Multiply and take the square root, the X that we get. 1.2 times 10 to the minus second. That amount that we just got there, marrying back to this table, is our X value. That's our OH minus concentration. So now we have it. Now all we have to do is validate the assumption. We're looking for that to be less than 5%. Working that out comes out to 3.65. It works. There is no doubt. I can use the assumption. No quadratic, nothing. You can certainly, at this point, work the quadratic because the number you're going to get is going to be virtually the same as the one you would get not doing the quadratic. It's a lot simpler though to look for the assumption and go right there. Okay.
On the test, will we need to do quadratic as well as?
No, on the
shortcut?
test, if you can use the assumption, you use it, but there'll be at least one on the test where you have to use the quadratic. There's no choice.
Fair enough.
So, if it's over 5%, you're gonna wanna go back?
You go back to this point here, and you make it a quadratic. The two things, for most of these assets, the quadratic can be avoided, because this is right around, they're all around -4 or better, and these concentrations are fairly high. That's enough to spin it around and get us out of the quadratic. They punish you with the quadratic more in the chapter 14. Here, keep finding sticky ways around it, you go with it. Because mathematically, it doesn't matter, you get the same number.
I was just scratching my head.
If we look at this, that tells us that our hydroxide ion concentration is 1.2 times 10 to the -2nd mole per liter. They still want us to find the pH, so I can find the pOH while I'm here. The pOH of this is 192. And then while I'm here, remember, we'll use this equation all the time with the bases. We add the two together, we get 14. Essentially 14 minus this. And even though it is still a weak base, it still gives a fairly profound pH, and the pH is 12.08, certainly on the high side. So everything that we derived about the acids works for the bases. They're mirror images of one another. The difference is, at this last step, you have to convert from pOH to pH. That's what they're asking you for. Questions? Avoid the quadratic if it is mathematically feasible. Can you get around it? Step around. The last part of the chapter talks about the acid-base property of salts. When we look at salts, we talked about or seen salts from the very beginning. Remember that a salt, by definition, salt, we're talking about species that have positive and negative. When we talk about a salt, we're talking about a metal and a non-metal linked together. Talking about a positive species, negative species. We have ionics involved. And that we know that salts dissociate water. For example, we know sodium chloride, when placed in water, breaks up to produce sodium ions, the chloride ion. What we want to know, this acid-base property of salts is, when we put these into water, do either of the ions that are released cause the solution to become acidic or basic? In order to do that, we have to separate the field. We're going to talk about the anions, we're going to talk about the cations, and what links the two together. Talk about the anions first. That is the negative species. One of the first rules that we'll notice is that in general, anions, when they're released, are either neutral, a weak base. That's what most of them do. They're either going to be neutral, that is, they do nothing, or they're going to be weak bases. There's a very small fraction of them that will be a strong base. But this is a very small group. So when we think about the anion, when we take a salt, we're going to see the problems that come along with this. We take a salt and we toss it in water. The negative species that's released is either neutral, does nothing to pH, or it affects the pH in a basic way. The way we can tell the groups are if the anion is from a strong acid. If the anion itself is from a strong acid, they are neutral. The anions of strong acids, the back half of the strong acids, are the chloride ion, the hydrosulfuric ion, the nitric ion, chlorate ion, et cetera, et cetera, et cetera. The table on page 725 shows the ones, and they actually show these three as being the most common. We'll mark under that. These three are the most common ones that we see that are neutral. ClO4 is a little complicated, so keep that one out. The big three are Cl minus, HSO4, and NO3. They're neutral. That table that's there, you would have that available. I don't expect you to sit there and memorize the table. The table's something you can look at on a test. But you'll see that those three are the neutral ones. The gross majority of that table that's on 725 are ending up being weak bases. And that's that, if you look at that table, there's the whole center. There's all different kinds of ions there. They're all purple. SO4 2 minus fluoride ion down the line. All of those are generally weak acids in general. At the very bottom of that table, there's just a couple, OH minus, S2 minus, and O2 minus, that are strong. Good.
You said it was on page
725, very bottom. So you'll see most of the anions, which when you look at the table, are on the right side of the table. Neutral, weak, or strong bases. That's the table. Again, table's in front of you if you're asked to deal with this kind of stuff on a test. That's what anions do. They're either weak bases, strong bases, or neutral. So you look at the table to find out which ones they are. The cations, on the other side, are the other half of that table. And if we look at the three possibilities for the cations,